Hi students, today we're going to go over notes for 2.1. We'll start off with vocabulary as usual. Our first vocabulary term is relation. A relation is a pairing of inputs and outputs. We typically think of inputs as x values and outputs as y values. Now a function is a relation where every input has exactly one output. So for a relation to be a function, each x value can only have one y value. Now, domain is known as our x values or our inputs. Range is y values or our outputs. Next, we're going to go ahead and look at some examples using this terminology. In example 1, it says, consider the relation given by the points 3, 2, negative 1, 0, 2, negative 1, and 0, 3. They first want us to identify the domain and the range. So remember, domain is x, range is y. So the domain will be all those x values in each point. X values are listed first. So we have 3, negative 1, 2, and 0. Our range are the y values, or the numbers listed second. 2, 0, negative 1, and 3. In part B, it says to represent the relation using a graph and a mapping diagram. So on a graph, they mean a coordinate plane. So on this coordinate plane, I'm going to plot these points. The first point is 3, 2, so I go over 3, up 2, and put a dot. The next one is negative 1, 0. Then we have 2, negative 1, and 0, 3. So the red dots are the points for each of these coordinates. Now a mapping diagram is where you have the two ovals. One will have the x values, one will have the y values, and then we use arrows to show which ones they connect to. So I'll start by listing the x values, 3, negative 1, 2, and 0. I'm going to list the y values, 2, 0, negative 1, and 3. Next, I'll draw arrows. So 3 in this point goes to the y value of 2. For the next point, negative 1 goes to 0. Then for the third point, 2 goes to negative 1. And for the last one, 0 goes to 3. And that's it. Is the relation a function? So looking at this, does every x value only go to one y value? The answer is yes, so this is a function. In the next set of examples, we're going to determine if the relations shown in these tables are functions. So the first thing I like to do by looking at the tables is see if any of the inputs repeat. Notice in this first example, the 3 repeats. That means the x value of 3 goes to negative 1 and it goes to negative 2. So our input goes to 2 outputs, which is not allowed for a function. So no, this is not a function. For the next one, none of the x values repeat. That's a good thing. If none of the x values repeat, that means they don't go to different y values. So this is a function. It's okay that the y values are listed twice. Y values can have more than one x value. That's all right. You can have duplicates in output or the y values, just not in input. Okay, so next we're going to go over the vertical line test. This is another way to tell if a relation is a function. A relation is a function if and only if no vertical line intersects the graph twice. And I'm going to show you what we mean by that. I'm going to give you 2 examples of graphs. Here's the first one. Here's the next one. So in this first one, notice, no matter how many vertical lines I draw through it, I will only hit the graph here at one point. So this would be a function. However, for this other one, I'm hitting more than 1 point with each vertical line. Notice I'm hitting 2 points. Since I'm hitting more than 1 point with my vertical lines, this is not a function. So let's apply this to the next example. It says determine whether each relation is a function using the vertical line test. So looking at A, I'm doing okay with these vertical lines here. I hit a hiccup at 2. So look here, we have a colored in dot for this point. This dot's open. So what that means is the colored in dot means it counts. The open dot means it doesn't count at that number. So we're still okay. It's technically only hitting at 1 point, which means that yes, this is a function. For the next one, if I start drawing vertical lines, notice over here on the right-hand side, I hit more than once. So no, this is not a function. Next, we're going to go over some more definitions. So we have independent variable. An independent variable is the input variable, also known as x. Dependent variable is the output variable, also known as y. Now, the reason they're listed as independent and dependent, I'm going to go ahead and show that now. If we have y equals 2x plus 1. So here's an equation with the two variables, x and y. The y value depends on what you plug in for x. So y is dependent because it depends upon what the value is for x that you plug in. X is independent because it doesn't rely on another value to determine what it equals. In example 4, we're going to go ahead and graph a linear equation. So we have y equals 3x minus 5. Now recall in slope-intercept form, that's what this is called. Oops. You have a slope and you have a y-intercept. So here, m is the slope, our m is 3. B is the y-intercept, our b is negative 5. So you always want to start at b. So on the y-axis, at negative 5, I'm going to put a dot. Our slope, 3 over 1, means we rise 3 from that point I just plotted and then run 1. So I count up 3 over 1, up 3 over 1, up 3 over 1. And you continue that pattern as far as you can. Draw a line through your points with arrows on both ends. Any questions? Oh, sorry, I get used to teaching in normal class. I'm asking you guys to have questions. If you do, you can go ahead and contact your teacher. Okay, some more vocabulary. A linear function. A linear function is a function that can be written in the form y equals mx plus b. So it's an equation of a line. Now we do use special notation for an equation when it is in fact a function, for when every input has exactly one output. And that function notation is f of x. Okay, so it looks like this, f parentheses with x inside. When we say it as f of x. And this means the value of the function at x. Okay, so it's just another way of saying y. We replace y with the f of x. So look here in example 5, we have these functions. Notice they used f of x. Normally we would just put y there. It means the same thing technically when you're solving. It just indicates that these will only have one input. Every input will only have one output. So here it says tell whether the function is linear and then evaluate it when x equals -3. So to tell if it's linear, it needs to have an x that has an exponent of 1. It can't have any other exponent. So looking at A, f of x equals -2x cubed plus 5. Because of that cubed, it means it's not linear. Okay, so it's not linear because of the cubed. I can still solve when x is -3. So to do that, I'm going to replace every x with -3. Notice here in the function notation, I put f of -3. That just means that this function at -3 is going to equal -2 times -3 cubed plus 5. The left-hand side stays the same. We only simplify the right-hand side. So -2 times -3 cubed is -27 plus 5. -2 times -27 is a positive 54. And 54 plus 5 is 59. So this function, when x is -3, equals 59. This gives you an x value and a y value. In example 5, part B, it says g of x equals 12 minus 8x. It's okay that it's a g instead of an f. It all means the same thing. So in this equation, x has a power of 1. It's just not written. If you look, this is like slope-intercept form. It's just that it's written with the constant first. So yes, this is linear. And then to evaluate it when x is -3, I replace all the x's with -3. Remember only to simplify the right-hand side. So 12 plus 24, because it's a -8 times -3. And this will equal 36. So when x is -3 for this function, y is 36. And that concludes our notes for today. If you have any questions, be sure you contact your teacher.